Hello, my name is Alexis Mesa. This is a video for my image processing class. This video is going to consist of a presentation followed by a 4 video MATLAB demo. My project consists of a CAMSHIFT algorithm, which is an improvement from a MinShift tracking algorithm. So the motivation behind it is to find a filter which is able to do face tracking and simple object tracking or block tracking. One way of doing that is the MinShift algorithm, which through the years has provided a reliable way of tracking object whose appearance is defined by color. However, it's not limited to that. It could use just the edge or the texture of the image. To explain a little bit about MinShift algorithm, the idea is that it takes the intensity as the XY coordinates and divides by the distance from the center of the feature window, which is the blue line. This results in a new center of mass with a displacement seen by this arrow, which is the MinShift vector. Now, the motivation of a CAMSHIFT is that the MinShift creates many errors since the window does not change in size. For example, if the window is too small, then the prediction will jump inside the object of interest, since the window is just a small subset of the whole object. Also, if the window is too big, the algorithm will get confused and will not know what object is tracking, if it's the ball or the background or the tennis ball. Hence, to fix that, I propose a continuous adaptive shift algorithm, MinShift algorithm, which changes the windows according to the size of the object tracked. So how does the CAMSHIFT works? The first thing it does is it asks the users to pick a target to be tracked. Then it produces a histogram based on the hue of the whole image. Then increases the region of interest. It iterates the MinShift algorithm until it converges. In my algorithm, it converges when it reaches 1 pixel error. Then it uses the calculation in step 4 to produce a new size of the window, and then it jumps to step 4 to keep calculating the next frame until the video is over. In order to do this, the zero moment is calculated by summing the XY coordinates of the intensity. Then the first moment is computed by multiplying the X and Y components of the image intensity. Then they're normalized to give a centroid, and the window size is just the square root of the zero moment multiplied by a ratio which was experimentally obtained. Now, why do I pick hue? The reason is that it behaves really well at color detection. The hue, for example, this is a red object, and this is a hue image of the object. As you can see, it's really easy to distinguish between that and the background. In fact, once the region of interest, which is picked within the black box, is calculated, everything else on the background is omitted, hence it's turned black. But there's an issue on calculating the region of interest. I made an optimization about it, because usually what is done is that all the pixels, the intensity of all the pixels within the region of interest is is there's sum and divided by how many pixels. Basically, the mean is obtained, and in cases such as this, produces good results. However, in cases such as where the user picks a lot of background space or space that is not within the that is not inside the object of interest, it produces bad results such as this. The reason why is that the background mean hue is a lot lower than the tracking object. Hence, once you combine, because the mean, these two, you get an undesired resultant hue. To alleviate the problem, instead of using the mean, I use the median, since it is assumed that the user is able to select at least 50% of the object. Hence, the window consists of at least 50% of the object of interest. Now, a few things about this algorithm is that it continuously adapts the window to increase to fit the size of the object, so that it encompasses the whole object, as long as the object has a contiguous color. Furthermore, another really important characteristic of this algorithm is that it's able to compensate for objects that are moving in different depth. Hence, in a mean shift algorithm, if the objects move in different depth fields, the algorithm will fail, because the window will start picking up, for example, over here, will start picking up background pixels, and will say, oh, I lost the target, when in fact it's within the target. Hence, this algorithm is able to change the size as it moves towards away from the camera. As you can see, it moves the feature window, it gets reduced and it moves away, and as it moves forward, it starts increasing in size. Hence, the CAMSHIFT algorithm shows a significant advantage. In conclusion, the CAMSHIFT algorithm shows a significant advantage over the mean shift algorithm with little computational overhead. Only 2 additional square roots and 2 multiplications are needed in order to obtain a continuously adapting feature window, which are just these 2 over here. Hence, it's a small price to pay for such an improvement. Now I'm going to do a demo. Basically, there are 4 different videos. The first one shows how the CAMSHIFT provides the same capabilities as the mean shift algorithm. Demo 2 shows some interesting characteristics about the CAMSHIFT algorithm. Demo 3 shows the same as Demo 1, but with a faster moving object. And Demo 4 shows how the adapting window size works. So here's my MATLAB demo. I'm just gonna run it. What this does is it enters each of the folders and extracts the frame. After that, it asks you to select a feature window. You can see I'm gonna select the red object. Now it calculates where the object is going to move according to the frames. This window should close, but this computer is really slow, so it doesn't update the screen very often, I would guess. Now, as you can see, the algorithm effectively tracks the object. The feature windows changes according to the movement of the object. Now it's going into Demo 2 folder, which is another video of this marker. So I'm going to pick a feature window, and it's going to start calculating the output movie for that specific input. As you can see, it follows the object correctly. However, it's really interesting that over here it doesn't move much until it reaches the very end of the marker. I made a couple notes about it on the report. Now the third demo, for the third demo, I'm gonna select the ball. This is gonna take a little bit longer because this demo is about 20 seconds long. Although this algorithm is not implemented in real time, it could easily be implemented, transported to C, and be implemented in real time, probably with a GPU. So it's very portable. Okay, so the movie is ready. As you can see, it follows the object correctly. Even though the object is moving relatively fast, the CAMSHIFT algorithm has no issue solving that. Now the third algorithm is really important because it's a really good improvement from the CAMSHIFT algorithm. So basically what the marker is going to do is just move away from the camera and then move towards the camera. In the main shift algorithm, as the marker move away, the algorithm will fail because it will start picking up the background pixels since the size of the feature window never changes. Now I'm going to pick this feature window and it's going to start calculating. Let me close this one. Oh well, close that for me. As you can see, the feature window it becomes smaller as it moves away. Really small. Actually, it becomes a 3 by 3 pixel window at the farthest point. So this is my whole demo. I hope you enjoy. Thanks a lot.